Okay, so we talked about sugars. So now let's talk about another group of food, fats, and how we break those down to get to energy. So a large amount of energy is obtained when fatty acids undergo oxidation in the mitochondria to yield or make acetyl-CoA. And these fatty acids undergo beta oxidation, and this removes 2 carbon segments, one at a time, from the carboxyl end. Okay, so I say it choose 2 off the CHO end, because this in my brain registers as CHOO instead of COOH. Regardless, you take 2 carbons off the carboxyl end. You chew 2 off the CHO end. So let's learn how to describe the metabolic pathway of beta oxidation, calculate the ATP for the complete oxidation of a fatty acid. All right, so in stage 2 of the fat metabolism, fatty acids undergo beta oxidation, and this removes 2 carbon segments from the carboxyl end. So each cycle in oxidation produces acetyl-CoA and a fatty acid that's shorter by 2 carbons. So fatty acid activation, this prepares fatty acids for the transport through the inner membrane of the mitochondria. And this combines a fatty acid with coenzyme A to yield fatty acid acetyl-CoA. And this requires energy that's obtained from the hydrolysis or the breaking of 2 ATP to give you AMP and those 2 PIs. Because remember, ATP is 3 phosphates and AMP is 1, mono versus tri. Okay, so you have your fatty acids, your acetyl-CoA synthesis, and your fatty acid. Okay, and then AMP, etc. So the reactions of the beta oxidation cycle in the mitochondrial matrix. The fatty acetyl-CoA molecules undergo beta oxidation in a cycle of 4 reactions that convert the beta carbon, CH2, to a beta keto group. And once the beta keto group is formed, 2 carbon acetyl groups can be split from the carbon chain, shortening the fatty acid chain. Basically, this is saying, okay, we're chopping 2 carbons off the carboxyl end. It's telling you at the beta carbon. You have the alpha carbon, which is the first, and then the beta carbon, which is the second. It's chopping it there, and you're taking 2 off of the carboxyl end. So reaction 1 is going to be that dehydrogenation. And hydrogen atoms are removed by FAD from the alpha and the beta carbons, and they form a trans carbon-carbon double bond and FADH2. So we talked about the order, alpha, beta, last week, right, in those chapters, and we talked about cis versus trans. So remember, cis fatty acids have the hydrogens on the same side of that double, the carbon-carbon double bond. For trans, we have 1 hydrogen on either side. So cis tends to be kinked, where trans fats tend to be straight because those hydrogens aren't fighting for space. And so the trans fats are the ones that we hear about a lot in the news that aren't the best because they tend to stack like a saturated fatty acid. All right. Reaction 2 is going to be hydration, and this is where the hydrogen OH is going to be added across the double bond, and this forms the OH adding onto the beta carbon. So basically, we're finishing off that chopped end. Okay, so we're going to chop here between alpha and beta, and then we have to end up, remember, we're producing FADH2, so this would be the oxidation of it, and then the hydration of it, where we would be adding on the water. So then reaction 3 would be oxidation. So this secondary hydroxyl group, that OH on the beta carbon, is oxidized to yield a ketone or a keto group, while the hydrogen atoms reduce the coenzyme NAD+ to NADH and H+. So this is that oxidation reaction that you can see here. Reaction 4 is cleavage, or the actual chopping, okay? And so the alpha and the beta carbons, that bond there is going to be cleaved or cut to yield a 2-carbon acetyl-CoA and a shorter 8-carbon fatty acid, acyl-CoA. And then the cleavage is repeated until the fatty acid is completely broken down to form acetyl-CoA. Then the acetyl-CoA produced in the fatty acid can directly enter into the citric acid cycle that we just learned about. So it's really cool. So we just need to learn like how to get to the commonality of acetyl-CoA from sugars to fats to proteins. And from there, all of the reactions are going to be the same. So here are the fourth reaction. So you're going to see each time we're chopping off 2 carbons from the carboxyl group, and it's getting shorter and shorter and shorter. So you can see this is CH2, 2, and then just that. And then at the last one, we actually end up with 2 acetyl-CoA. It's kind of like if you have one last piece of cake and you cut it in 2, you're only making 1 slice, but you end up having 2 pieces. Same analogy. Okay, so this comes into play when we talk about calculations. So let's do a quick little study check. So let's match each of the following with one of the reactions in the beta oxidation cycle. So pause me and come back. All right, so water is added, hydration. When I'm drinking my water to stay hydrated, okay, we're adding water. FADH2 is forming an oxidation, kind of like what we talked about in aerobic metabolism, right? When a 2-carbon unit is removed, that would be when the fatty acetyl-CoA is cleaved. And then when we form an NADH, that is going to be through oxidation. Okay, so your cycles here, the number of beta oxidation cycles depends on the length of the fatty acid, and it's 1 less than the number of acetyl-CoAs. So basically, if we have a number of carbons and you divide it by 2, that gives you the number of acetyl-CoA that are going to be produced. And if it asks for how many rounds, you take that number and you subtract 1. So it's the number of carbons divided by 2 minus 1. I think of little minions, because I love minions, sitting there in a boxing ring with like round 1, right? So for rounds, you're going to subtract 1. And so these are just a couple examples. 18 divided by 2 is 9, so you're producing 9 acetyl-CoA from an 18-carbon fatty acid in 8 rounds of beta oxidation. Right? Great job.